Hello, hello.
We'll be starting soon. We'll be starting soon with the fifth day of ISLA within 2 to 3 minutes after more participants get in.
Once again, those who are here, I would like to see your faces, even if you are having breakfast or lunch or anything according to your time zone. This is the last official lecture of the school. This one, the turnstile. Turnstile symbol. That's double turnstile. This is single turnstile. Yes.
Naturally, it stands for syntax and that stands for semantics.
So how do you write it? Turnstile xy.
Truth turnstile in the context xy. X dot y is equal to y dot x. Yeah, we can start. I have so many things to say.
Welcome everyone to the 6th and last day of ISLA 2022. So we'll begin with an official lecture by Dr. Amit Kuber. We'll be speaking about syntax-semantics dualities, the first two of which you have seen the previous 2 days. The last and final lecture will be delivered by him today. Over to you.
Thanks you. So not just thank Anay, but everybody who has survived these hardships throughout the week. Okay, so yesterday we saw we started looking at alphabet for first order logic. And we saw what is meta language and language, and we chose a very, very careful approach. Yeah, that we have to write these quantifiers and connectives in a very spatial order. And then we saw there are some classes of categories which are increasingly complex. And according to the Horn theories, Cartesian theories, regular theories, coherent theories, and full first order theories, and correspondingly we have classes of categories which contain more and more categorical structure, and corresponding to that we also saw that the subobject lattices have got richer structure, subobject posets have got richer structure. So today we will be mostly focusing on the Horn theories. So let me quickly remind you what it is. So truth and conjunction, yeah, and some Cartesian theories. So Cartesian use some existential quantifiers, but not all of them. I will describe what they are, and after that, when we have enough structure in our category, then how can we interpret, we saw how we can interpret complex formulas in our structure. So this is simply a revision of what subobjects are. Yeah, subobjects are isomorphism classes of monomorphisms whose images are the same, essentially, right? Then if your category happens to have finite limits, then we can construct pullbacks of subobjects, which will give you intersections or meets of subobjects. So it becomes a meet similarity with a top element. Yeah.
Pullback is it is an assumption.
Yes, existence of pullbacks is an assumption because if finite limits are present, then pullbacks are present. Yeah, in particular, pullbacks are finite limits, right? So we have that kind of structure, and we also saw how we can interpret quantifiers as adjoints. I am aware that this is by no means easy to understand in the first go, but the idea was simple, that we collect all those elements in the codomain in whose fibers there exists an element of A prime. That was existential quantifier. And for all we collect all those fibers all those elements whose fibers are entirely contained, means for all elements in its fibers, they are contained inside A prime. So that is the idea of existential quantifier and for all quantifier. Very quickly, geometrically, the existential quantifier simply corresponds to projections onto lower dimensions. Okay, that's all. No, I'm talking about, like, if you are thinking about R square to R, then there exists y phi xy. So if phi xy defines a subset, let's say circle, then there exists y phi xy defines its projection onto x-axis. So existential quantifiers are important in that sense. Right. And then we started looking at how to interpret different terms in context and formulas in context. Okay. So the interpretation, first of all, some people, told me, offline participants told me that it was not clear what the context was. Context, so Purvita defined set of variables for a term and a set of free variables for a formula. Right? So if you remember that, then a context is any finite set of variables which contains variables for all the terms used and all the formulas used there. Free variables for all the formulas. Yeah, bound variables don't really matter. So if we for categorical logic, to make our life simpler, we use this sequent notation, yeah, which is written here. If you can see this way, this is where the sequent notation is written. Because we want to avoid talking about for all quantifiers, they are the most complex in that list. We want to avoid talking about them. So once we set this context, then the interpretation of terms in context is simply the projection map. The interpretation of function symbols is this composition. Yeah. So interpretation of terms is always going to be a function from m to the power length of x bar to m. And this is the composition. And then the interpretation of formulas in context is, we started doing that, and we just did this simple formula where one term is equal to another term. Yeah, that's a formula. And for that we used equalizers. Yeah, if we assume that our categories have finite limits, then in particular they have equalizers, so we can interpret such types of formulas. And what is the interpretation of this sequent notation, this turnstile notation? That the it's written here. I will show you that the interpretation of this formula phi1 in context x bar is less equal the interpretation of formula phi2 in context x bar. And then we saw some examples. Yeah, this was the theory of groups. We wrote them as commutative diagrams, and we said that if you interpret this theory of groups in various settings, then you get something different. And these are mathematically interesting objects. All right. Any questions until this point? Okay, in that case, I'm going to.
Just one thing.
Yes.
Cross product is what do you call? Is it
The cross product is these are binary products these are categorical products. The cross products are categorical products, right? They have that universal property.
therefore the projection is very.
Yes, the projections onto each components are well defined. Now, I should warn you that in ordinary categories, these projections are not necessarily epimorphisms. Epimorphisms means the categorical versions of projections. Yeah, they could be any morphisms, but they satisfy the universal property. All right, so now what is remaining in the hierarchy of formulas? If we want to deal with all atomic formulas, yeah, which means they do not use any quantifiers or connectives, then we have to look at so equalizers we have already done, equality we have done. So the next type of formula that we can use is this. So x bar dot r t1 x bar t2 x bar, sorry. It becomes difficult to control this on the boundary. T2 x bar up to Tm x bar. Okay, let me finish writing this in the top line and then I will go back. So where I'm assuming that the arity of r to the power m is arity of the relation symbol r is m. All right. So what is the context here? The context is x bar. So we need a sub-object of, and let's say our model is this. So this is our formula, let's say phi x bar. Yeah, this is our formula phi x bar. And I want to determine when does a categorical structure M satisfies this formula phi x bar. Yeah, this is my quest for now. So, as I said yesterday, terms will be interpreted as morphisms and relation symbols as well as formulas will be interpreted as sub-objects or monomorphisms. Yeah, because in the standard setting, they are subsets. So this is the natural generalization. Okay, so R has arity M. Okay, so which means the interpretation of the relation symbol Rm, relation symbol R in the structure M is a monomorphism from Rm to M to the M. Yeah, this is given. And what do we need? We need M to the power size of x bar. We need a subobject of that. Yeah, formula in context is always going to give me a subobject. So this is x bar dot phi. Its interpretation is going to be a subobject of this. Now, the way I have written this, do you have any guess? Pullback, exactly. But for constructing this pullback, we have to construct this morphism. In order to construct this morphism, I first need to fill up this. And this data is given by the terms, the interpretation of the terms. So recall that a morphism to M to the power M is an M tuple of morphisms to M. Small m tuple of morphisms to capital M. Yeah, very bad choice of notation over here. Okay, so this is interpretation of x bar dot T1 This is a morphism to M and dot 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 interpretation of X bar. I should use double brackets, X bar dot TM M. So this tuple of morphisms is what I take. I already have this map monomorphism from Rm to M to the power M, and then I construct this pullback, and this pullback is going to give me this vertical morphism, which is the interpretation of this formula.
So therefore, pullback is a hypothesis.
Yes, so we are working, while we are doing all this, we are working with the basic assumption that our categories have finite limits. So finite limits include binary products, terminal object, equalizers, pullbacks, all of them. Yeah. Without that, we can't do anything. And of course, we need products to construct even M to the power small m. So all of this is necessary. And this is the minimal we can hope for. Yeah. It's not really a lot to ask for finite. I'm still working with Horn setup. In fact, this is even smaller set of formulas. These are only atomic formulas. I have not started using any of the quantifiers or connectives yet. Okay, so now once you know how to deal with equality as well as relation symbols, we have covered all of the atomic formulas. Now from atomic formulas, the next step is always quantifier free formulas. Yeah, the quantifier free formulas. So suppose I have got one formula in context X bar dot phi 1. Its interpretation is going to be some monomorphism to M to the power X. And another thing is, let's say I have got another formula in context, which is phi 2. And suppose they have the, so I can assume safely that X bar is a context which is suitable for both of them. Now, if I wish to construct, yeah, this is where yesterday's lecture will kick in. So if I wish to construct the interpretation of X bar dot phi 1 meet phi 2 in this, then I will declare it to be, so I have got two subobjects. I want to construct a third one. What's the idea? I should take
pullback and
no, I mean pullback is the idea
meet
to
up these two.
construct it, but see, I'm working inside. This is all happening inside the appropriate category, the subobject poset of M to the power X bar. And this is what I have to use. The subobject poset in a Cartesian category, which means the category with finite limits, has got meets. So I will define it to be the meet. In the subobject poset. See, this is precisely what we do even in propositional logic, isn't it? That we interpret conjunction as and. So here we are interpreting conjunction as some meet operation, which is the natural choice to do. Now, if I change this symbol to disjunction and I have the categorical structure of a coherent category, then I can change this to disjunction. If I have implication, then I can change it to implication. You can see similarly if negation happens to be there, and I'm emphasizing on the fact that this negation and implications, they could be iting implication and negations, which we saw yesterday in Nick's lectures. Then I'm going to use in that appropriate iting algebra, the iting negation as well as the iting implication for these formulas. So that's how I can deal with connectives. It's really very simple. Once you understand that the richer categorical structure gives you richer lattice theoretic structure, then it's simple. In the classical setting, if you have the category of sets, which is a particular case of a Boolean category, then all the subobject posets are in fact Boolean algebras, and all these things are interpreted as usual. Yeah, Boolean implication, Boolean negation, and so on. So my point is that we can interpret all these things in a way that is consistent with our already existing understanding. Any questions? Okay. If there are no questions, let's go ahead. Now, what remains to be shown? If we had dealt with all atomic formulas and connectives, then we are done with all quantifier free formulas. So what remains now? Existential quantifier and universal quantifier, correct?
So what is universal quantifier?
For all?
For all, right?
Yeah, for all is the universal quantifier. Right, so suppose I am given, now I have to write down this formula very carefully. Suppose I am given a formula in the context x bar comma y, I am given the formula psi x bar comma y. This formula is given. And because I know this formula, this is less complex than the existential quantifier. So I can assume that inductively I have already constructed its interpretation in the structure M. So I already have this from to m to the power length of x bar plus 1. Yeah, because I should be writing length of x bar comma y, which is length of x bar plus 1. Y is a single variable. I'm just going to deal with a single variable single variable existential quantifier. All right, so from here I have got this natural projection map onto first length x bar coordinates. Yeah, so I'm going to call that projection map pi, and this is down to m to the length of x bar. Any questions here? We are simply taking the projection from m to the length of x bar plus 1 onto the first length of x bar coordinates and ignoring the last one. And now, what is my goal? I want to obtain, let me write that, I want to obtain in the context x bar, I want to obtain the interpretation of the formula there exists a y such that psi x bar y. I want to obtain the interpretation of this inside M, which is meant to be a sub-object of this. Correct? Because it always depends on, this is a sub-object in the context x bar comma y, it is a sub-object of M of length of x bar plus 1. This has to be a sub-object of M to the length of x bar. So what should be the idea here? I want to obtain this arrow. And suppose I am working in a regular category. I'm working in a regular category. So I have got finite limits as well as, do you remember anything from last?
Images of the morphism.
Images of the morphism, exactly. So if I construct this, if I take this composition, the horizontal composition, and I construct the image of that, then I will get this image object, and that is precisely my interpretation of existential quantifier. In other words, this is equal to, there exists sub pi of this. You can check it with your yesterday's definition. So you remember that I had sub-object of A, sub-objects of B. There is a pullback, like F inverse kind of thing happening. So if I'm given a sub-object of B, then I can obtain a subobject of A. And then I defined that there is a left adjoint. In a regular category, this map pullback has a left adjoint, which was there exists sub F. Now here also we have a similar setting. This is my map. This pi is my map, and I'm simply going to push it via this left adjoint, and that is precisely the definition. It is the image. We also saw this, that it is precisely the image of this subobject, this composition. So in this way, we can obtain the interpretation of existential quantifier. I don't have enough time to show you how it works in an example, but this should also give you an idea what we can do with this. So suppose I want to construct X bar. Instead of there exists, I will take for all. Then that will be the for all pi. If my category happens to be a pre-topos, then I will have a right adjoint to the pullback functor, and I can use that on this particular subobject. So that is the definition, that is the construction of this. Okay, so quantifiers are complicated. You have to get your hands dirty to properly understand them. But I can show you something over here. So let us come back to this example and let us do, yesterday I think we did something like this equivalence relation during tutorial. Yeah, the theory of equivalence relations. Let us at least try to write down what happens with, so let's say less equal is my language. It only consists of a binary relation symbol less equal. And I want to write down what is the meaning of less equal XX. Yeah, this is a formula. And the sequent is this. Yeah, the sequent says that tautology entails in context X less equal XX. What does this stand for? Reflexivity, correct. Are online participants sleeping or awake? I'm not getting even simple answers. Do we not require? That is precisely why we adopted this context notation, a sequent notation. Yeah, whenever I say that it is in context X, then I can avoid the for all quantifier. All right, so the definition is in front of you. Less equal, as you can see, less equal interpreted in M is going to be a sub-object of M square. But I only want M to the length of X bar. What is the context here? Just X. So I only want M over here. Right? Then what is my map here? Yeah, the map is X goes to X comma X. But I cannot write that in categorical language because there are no elements. So what I should write? It is identity of M, comma identity of M. So this is projection. The only projection possible, I'm taking it twice. Because the interpretation of term X is the first projection. Interpretation of term X is again the first projection. That is my identity. Then I will construct a pullback. And that pullback will be my, I should write this X dot less equal XX. And its interpretation. So this vertical morphism is what I need. This vertical morphism is my interpretation of reflexivity axiom. What does this say of the reflexive? So what is the interpretation of this sequent now? The interpretation of truth symbol, a tautology, is the largest possible subobject of M, which is M itself. So this says, let me use a different color. This says that the subobject M, which I'm going to write as M, this is small m, let's say. So this subobject 1M is less equal M. But when can this happen? Again, tautology is the largest subobject in the subobject poset. So this can happen if and only if it is equality. So it means this sequent is true in M. We write it like this. This sequent is true in M if and only if this arrow M equals identity. Okay, in other words, you will get that the diagonal factors through the interpretation of less equal. This is our usual definition, right? The diagonal x comma x factors through the order, the graph of the order relation. Yeah, it might look like a very complex, convoluted way of doing something like as simple as reflexivity, but it's worth it because it gives us a lot of flexibility. Yeah, so using this, you can construct internal orders. You can construct internal equivalence relations. Yeah, so this is a very nice way of doing things. Even if you don't have, even if your category is not concrete. Yeah, so groups, rings, vector spaces, these are all concrete categories. They have an underlying set structure, and top of that, there is some extra structure. But even if your category is not concrete, you still can talk about equivalence relations. If your category is regular, you can still take quotients by equivalence relations of objects. All these things are really interesting in various ways because they give you flexibility. Even if you don't have any control over the internal structure, you can do the mathematically interesting constructions in a given category. And that is why categorical semantics is a vast generalization of how we normally see things, how we normally interpret things, what is our usual semantics. Any questions? Oh, there is something in the chat. Thank you. Yes, in other words, the pair of maps of the relation have a common right inverse. Correct. Alternatively, a reflexive digraph of jointly monic pair. Correct. Yeah, I just feel, Professor Partha, that this is a bit too advanced to talk about these things. They are jointly monic pairs, and yes, you are right. You are absolutely right. But I'm trying to keep it as simple as possible. Thanks. Any other questions from online or offline participants? Okay, so let me tell you that this allows you to do lots of things. Let me remind you, probably I said this thing during the discussion session on category theory, but this allows you to do forcing, for example, which proves that certain statements can neither be proved nor be disproved. You can construct models of consistent theories by forcing them to exist in a certain model. You construct such models, yeah? In topos theory, you have the possibility of doing that using Grothendieck topologies. Moreover, as I already mentioned, you can also do synthetic differential geometry because you can define what is a natural numbers object. You can define what is a real numbers object. So for example, let me say something about this. So I'm going to talk about a natural numbers object very quickly. What are natural numbers? Yeah, in their very simple sense, there is a zero element, right? So there is a morphism named 0 from the identity to n. Its image picks out the least element, right? And moreover, we have this induction principle. The induction principle is nothing but a map from n to n. I'm purposely not writing our blackboard bold n. I'm not talking about the standard natural numbers. Yeah, I'm only talking about a natural numbers object. So it has a shift map. Now, what happens with this shift map? You can see that if I take 1 and n and this n, look at the images of these two maps. The zero map and this shift map together cover the entire natural numbers. The images of them cover the entire natural numbers. I will demand that this diagram is a coproduct diagram. Okay, this diagram is a coproduct diagram. And similarly, I will demand that whenever I'm given these two maps, so another property of the shift map is that it doesn't have any fixed point. Correct? So if I write identity morphism on n and s, then their co-equalizer is the trivial map. There is no co-equalizer possible at all. They do not become equal ever. This is what is expressed by this co-equalizer diagram. So these two, so pair an object n with these maps 0 and s together with these restrictions that this is a coproduct diagram and this is a co-equalizer diagram. This is your natural numbers object. Of course, many other things can satisfy. For example, even in the category of sets, natural numbers plus integers with appropriate shift maps. Yeah, you take a copy of natural numbers and put a copy of integers after that. Each natural number is smaller than each integer in this copy. Once you take that with shift map, then also it satisfies all the conditions. These are called non-standard natural numbers. So there are ways of interpreting natural number objects. Then you can also imitate the construction of fraction field construction, and you can do a lot of things. So this gives you a lot of possibilities. You try to isolate some categorical properties from this, and then you put them in any category, and that's how you can do synthetic differential geometry. All right, so now that we have established, I hope I have convinced you that doing categorical semantics is not just interesting, but also important. It plays a significant, it has played a significant role in our understanding of, means our semantics.
No, just
yes.
You obtain non-standard natural.
You can also obtain the standard natural numbers. That is one model I gave. Huh?
This is the standard one.
The standard one is just ordinary natural numbers.
The
successor is +1.
Okay.
Yeah.
So that is the standard one.
That is the standard one. I gave you one non-standard model, n plus z, in the category of sets.
And we can subset the rational numbers.
Yes, you can do all those things. Yes. All right. So logic, as we said, has two different parts: syntax and semantics. So we have seen how to do semantics with categories, with whatever structure available, whatever categorical structure available in there. Now we want to do syntax. And if I have syntax, then I should ask for a proof theory. There is a well-defined notion of a proof. There is a well-defined notion of a proof system in categories, appropriate classes of categories. But for today's lecture, yeah, just to keep things simple, I have decided I will only work with Cartesian categories. Yeah, they are the simplest class of categories and Cartesian categories, and I have already done some homework. Yeah, I came here early and wrote these things down as if these are my slides. So if I'm given a Cartesian theory or a Horn theories you all know now, they can use only truth and conjunction. Cartesian theories can also use some existential quantifiers. Okay, so I cannot explain everything in detail, but remember this. Yeah, I hope this helps, that these are provably unique existential quantifiers. Okay, so if there exists something, then that has to be unique. Yeah, we all write this symbol. Yeah, this is familiar to all of you. There exists a unique thing. And this unique thing, I should be able to prove from the theory, from my axioms, that there exists a unique thing. So for example, yeah, in group theory, we say that there exists an element in the group which is left inverse and which is right inverse. Even if we don't assume that those are unique elements, we can prove that such an element is unique. So I'm talking about something like that. All right. So given a Horn theory or a Cartesian theory, that is what is written here, we define its syntactic category. Now this syntactic category, I will quickly recall for you that these are just formal objects. Yeah, they do not have any meaning associated with them. Okay, so there is a notion of proof system, which means some formal set of rules, some axioms which we don't question, and a computer can manipulate these expressions. Okay, in that sense, now let us look at what the objects of this syntactic category are. This syntactic category objects are simple x bar dot phi, where phi uses only these things available: truth, conjunction, and provably unique existential quantifiers. For the discussion, we may as well assume that we do not have any existential quantifiers at all. We just have truth, and there exists, like these are Horn theories. A large class of ordinarily used theories fall under Horn theories. Yeah, for example, all algebraic theories, not fields. Yeah, fields have that weird axiom that unless x is non-zero, we cannot ask for an inverse. But rings, groups, vector spaces, modules, all those things fall under this category. Equivalence relations, partial orders, pre-orders, not total orders. So lot is being covered over here. What are the objects? The objects are simply alpha equivalence classes of such formulas in context. Okay, so this is a new term, alpha equivalence class. What does it mean? It means I can replace the variables with any other set of variables without questioning. That's all. Yeah, if at some point I need to, yeah, renaming of variables, that is allowed. I can replace x bar by y bar altogether. The only restriction is that they all should be distinct and the length should be exactly the same. That's all. Okay. Now, what are the morphisms? The morphisms from one alpha equivalence class to another alpha equivalence class is the graph of a function. See, we are not used to thinking about functions as graphs in general. But the graphs have some natural properties. So you can ignore this left-hand side for now, that the theory proves or the theory entails something. Just look at the right-hand side. The first axiom reads that theta x bar y bar, means the graph of the function, says that the first coordinate lies in the domain. So let me write something over here. Suppose my function goes from m to n. Now this m should be defined using the formula phi. N should be defined using the formula psi. What I'm saying that whenever a bar comma b bar belongs to the graph of the function, then a bar belongs to M. That is what this is saying. A bar belongs to M and b bar belongs to, sorry, I have made a mistake here. This should be y bar. Yeah, phi of x bar and psi of y bar. So a bar should belong to M, b bar should belong to N. This is, I'm rewriting the definition of being a function. Okay, then I have this, the functional thing, that this relation is actually a function. Associated to every tuple in the domain, I have a unique tuple in the codomain. So what is that uniqueness? Whenever x bar, y bar and x bar, z bar are in the graph, then I can prove that y bar and z bar are the same. Yeah, that is simple. This is the uniqueness criterion in the requirement or in the definition of a function. And moreover, I have to guarantee that given any element in any tuple in the domain, there should exist a tuple in the codomain such that that pair of tuples belongs to the graph. So that's the last sentence. Now, the only difference here is that whatever theory I have been given, that theory should prove this sequence formally.
That equality with dot.
Yes. Okay, that equality is dot. In fact, it is the conjunction over the length that yi is equal to zi. But I'm not writing that. Okay, so any questions about this? So remember, in stone duality, what did we say? Corresponding to every Boolean algebra, again, given any set of propositional variables, I can construct a Boolean algebra. There I was not talking about, like nobody else was talking about a theory. But then I introduced you in my first lecture that I can talk about a consistent theory. And modulo that theory, the Boolean algebra collapses to something smaller. Similar thing is happening here. I'm given a Cartesian theory T or a Horn theory T, and I'm collapsing it according to its provability. Collapsing formulas according to its provability. Now, this category that I have formed, I mean, I have just written down objects and morphisms. And at the bottom, I have also written down what is the composition. The composition is simply that there exists something in the middle which connects those two, which is a bridge. Now, why alpha equivalence is important, you can see that if at all in this definition of morphism, I was using x bar and x bar again, that would create confusion. I cannot really define a graph of a function like that. So that's why alpha equivalence classes are important. I will make sure that the variables used in the domain and codomain are always different. And similar fact is true for the composition. X bar, y bar and z bar are given. Then the formula reads that there exists a y bar such that theta 1 of x bar y bar and theta 2 of y bar z bar. This is how we define composition of functions ordinarily. Yeah, nothing great is happening here. Now, the interesting thing that will happen is because we have started with a Cartesian theory or a Horn theory, then this syntactic category will turn out to be a Cartesian category, which means a category with finite limits. And we can express them using logic purely. The terminal object over here is the alpha equivalence class of the formula tautology in empty context. Yeah, there is no variable used at all. It's just tautology. The product is simply take two disjoint sets of variables. So product of x bar dot phi 1 and y bar dot phi 2, where x bar and y bar are disjoint, is simply take their conjunction. Yeah, I mean, if I wish to write here, I can write phi 1 of x bar and phi 2 of y bar. Then this conjunction defines the product of these two objects. And similarly, there is an expression of equalizer. So once I have all these three things, then I have all finite limits, which means what we have proved that CT, the syntactic category, is Cartesian, or in other words, it contains all finite limits. Okay, so Cartesian theory or a Horn theory gives you a Cartesian syntactic category. Not a surprise now. Yeah, this was meant to happen. If I start with a coherent theory, then I will get a coherent category, syntactic category. If I start with a full first order theory, then I will get a pretopos. That's how we have designed this whole thing. Okay, so this is all formal. There is a proof theory which makes this work. This is syntactic category. So for Cartesian theories or Horn theories, we have understood this syntax properly. We know how to interpret those formulas, what is the semantics, but what are going to be the categories of models? That we haven't yet seen. Okay, so let me quickly remind you what we were doing earlier, that we had this kind of adjunctions. So I'm going to say Cartesian theories. And here I'm again going to write vaguely classes of structures. And if I put an op here, then I had the functor that models of that Cartesian theory, and on the other way, I had the theory, the common theory of all the structures present in that class. This idea is still there, but I have just put the word Cartesian over here. So in the remaining time, my job is to explain to you what is this other side? What are the classes of models? And from this dual adjunction for Cartesian logic, how we can reduce a perfect two-sided duality, how we can obtain a perfect two-sided duality. This duality is a celebrated result of Gabriel and Ulmer. Yeah, this is known as the Gabriel-Ulmer duality. I will state that. But for that, we have to understand something more about limits and co-limits. Are there any questions before I proceed about anything? Okay. For the last lecture, I shouldn't push anybody. It's too much to take in one day. All right, so let's go ahead. Now I'm simply going to recall what are limits and co-limits. Limits means cones over a diagram. Co-limits means cones under a diagram. That's at least that much intuition is clear. Now, suppose my arrows are coming from real numbers. I'm going to start with something very simple, reals with less equal sign. And suppose an is a sequence, is a monotone increasing sequence of real numbers. Okay, monotone increasing sequence of real numbers, that's all. Then basically what I have in the category, yeah, if I think of this poset as a category, then I have A1, then A2, then A3, and so on. One property that I want to highlight here is that given any two AIs, there is a common upper bound for both of them. Is that true? If I'm given An and Am, what is the common upper bound? A max of Mn. Right? Right. So now my question is, can something exist in the limit of this? Will there always exist something in the limit or not? I mean, limit as in co-limit, truly speaking. And under what conditions does it exist? Huh? If the sequence is bounded, then the limit will exist. Otherwise, it will not exist. But if at all the limit exists, if the sequence is bounded, then the least upper bound of this sequence is going to be my limit. Well, in categorical language, that's a co-limit, because there are arrows from here, 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 everywhere, such that whenever I have got arrows from everywhere, then there is a unique arrow from A to B, which means I'm simply re-expressing the property that it is the least upper bound. Yeah, of course. I mean, as we noticed earlier, if the sequence is not bounded, this A will not exist. But if the sequence is bounded, then this A will exist and it is the least upper bound. In other words, it is also categorical co-limit. But what was more important here, that given any two AN and AM, there is a common upper bound for both of them. Now, another situation. If I'm given a set X and I'm considering the collection of all its finite subsets, only finite subsets, then is that property still true, our desirable property, that given any two finite subsets, there is a common upper bound for both of them? Is that still true? And is it still finite? Yes, so it still works while we remain in this poset. This property is called being directed. Like anywhere you start, this and this point, eventually you are going to meet. Again, from here and here, you are going to meet. Eventually, everything comes together. Right? So this is a directed set. Is a directed set. What is a directed set? Let me quickly write down a definition for you over here. A poset P less equal is directed if for all AB in P, there exists a C in P such that A is less equal C and B is less equal C. Yeah, there exists a common upper bound. We are not asking for the least upper bound, just a common upper bound. So this is a directed set. Now, in this case, if I try to construct co-limit of the above, co-limit of the above, what do I mean? That what will happen eventually? What set will I obtain eventually? I'm starting with a singleton, another doubleton, then the common upper bound will be a tripleton possibly. Yeah, it contains both these things. And from everywhere there is a flow, and eventually I'm bound to get all elements of X. Now this co-limit will not exist inside this finitary power set of X, but it will exist in the category of sets. Co-limit of the above is the set X itself. This is the least, I mean, this is the least element that we can do. If you have seen more applications of Zorn's lemma, yeah, then and more or some applications of Zorn's lemma, then usually while verifying the hypothesis, what do? You construct directed unions. Those directed unions have a similar feel. Yeah, everything is coming together and then something happens. So this co-limit is known as a directed co-limit. Very roughly speaking, what is a directed co-limit? That you take a diagram in your category which has the shape of a directed poset. Okay, so whenever I have this A1, A2, AN as my original poset, if I want to take the shape of this in a category C, let's say, I will put an object in place of A1. I will put another object in place of A2, and in place of less equal relations, I will put a morphism. So this is F1, this is F2, this is F3, and so on. And then I will ask if the co-limit of this kind of diagram exists. Now, once again, as we saw in the first example, it may or may not exist. But if it exists, then it is desirable for us. Okay, so some highlights here that I'm only using finite sets. Yeah. Only using finite sets in this example. Finite or compact sets. And only using directed co-limits. So what I want to emphasize on, that every set can be obtained as a directed co-limit of finite sets. This property is not only true here, but also true in the category of groups, in the category of rings, in the category of modules. If you have heard of finitely generated, finitely presented objects in algebra, then in fact, I can also show that any finitely presented module, any module can be generated as a directed co-limit of its finitely presented submodules. Any vector space can be generated by looking at only its finite dimensional subspaces. And you consider this equality as your map. Right? So everything comes together. Yes. Huh? No? Where? Oh yeah, I mean, if you are going that way, that every vector space has a basis, so let's assume that. But I only need all its finite dimensional subspaces, and I take the union. Eventually, the directed union of all of them will be my, yeah. It requires axiom of choice, but still we can do that. That we can write down every vector space as something like this. Now, these are the properties which we want to abstract out in a class of categories.
Why are we fixing only finite here?
I'm not
Why are
going
we
to
talking
use
about
finite. I'm going to use the word finite, compact, or finitely presented. I will define it. In the standard setting, like a finitely presented group, for example, it has finitely many generators and only finitely many relations between them. But it's a beautiful idea that in category theory, we have a different presentation for that, and it coincides with this. They are equivalent. Okay, so any other questions about this? Okay, let's keep walking. We still have something more to do. Okay, all right. So suppose I'm going to do this very quickly now. Suppose I have this one sequence of morphisms indexed by natural numbers, yeah, and G1, G2, and so on. I have got two directed diagrams. I construct another directed diagrams. Let's say this is happening inside sets. Okay, I construct another directed diagram. Then what will happen? This is F1 cross G1. This is F2 cross G2, and so on. So suppose the directed co-limit here is A infinity, and the directed co-limit here is B infinity. In sets, we can always find directed co-limits. Yeah, that's a property of the category of sets. What will be the directed co-limit of this? Any guess? Confused, Vineet? Yeah, somebody in the audience?
infinity cross B infinity?
A infinity cross B infinity. Correct. If so, think about this. If you are confused, if I'm given a pair of monotone increasing bounded sequences, then what will be the limit of the pair of sequences? It will be the pair of the limits. So in other words, what I'm saying, that products, binary products, commute with directed colimits. This is a very important property, yeah, of the category of sets, in sets. So if I take two different diagrams and take their directed colimits and take individual, they are of the same shape, let's say, and then I take individual product everywhere, and then I take the directed colimit, it will be the product of the directed colimits of the individual diagrams. Not just that, yeah, suppose I have got these two diagrams, A1, B1, F1, G1, and I have this equalizer E1, and I have A2, B2, F2 and G2, and I have this equalizer E2. Then I can construct A1 cross A2, B1 cross B2, and F1 cross F2, G1 cross G2. What will be the equalizer of this? E1 cross E2. Very good. So what is this statement? Let me write this, that binary products commute with equalizers. Now I will ask something similar to you in a different color. Suppose I am given exactly same thing, but using co-products now. If I write down A1 disjoint union A2, and then I take the product B1 disjoint union B2, and then on the other hand, I take A1 cross B1 and A2 cross B2. Are these two isomorphic? Yeah, these two are not isomorphic, right? All of you agree? Just use the standard cardinality argument. You will easily see that this is not true, which means binary products do not commute with binary coproducts. So not everything commutes with each other. What commutes? Now this is where our main property comes into play. Yeah, and this is the basis of all syntax semantics dualities. This is what Mackay called logical doctrines. This word comes from Christianity, doctrines. These are some of the principles which a Christian has to follow, but now this is borrowed from there into mathematics. Okay, so Mackay's logical doctrines. The first logical doctrine for Cartesian logic, what is the logical doctrine? It says that finite limits commute with all limits. All limits means all products. Yeah, here I will write all products. Not just binary, even infinitary and equalizers, and directed colimits. Okay. So for Cartesian logic, now where is the word Cartesian coming into picture? On one side, yeah, I'm going to highlight this in green color. On one side, I simply have this finite limits, and on another side, I have these two. Finite limits is actually our syntactic categories. Yeah, you remember syntactic categories had finite limits. So these are, this is the syntax part. And the semantics part should contain all limits and directed co-limits. All right. So now I'm going to formalize this and then I will describe the category that I want to study. On the syntax side, what is happening is I'm going to consider this category cart. And on this side, I'm going to construct the category of locally finitely presentable categories. Okay, so these are not really categories in the ordinary sense. These are categories whose objects themselves are categories. Okay, so let me tell you what these categories are. So on this side, the objects are small. Small means the collection of morphisms is a small collection, is a set. Yeah, in general, we only require that home between two objects is a set. Now I'm saying the collection of all morphisms is a set. So objects are small Cartesian categories, means categories with finite limits. And morphisms are finite limit preserving functors. Between them, finite limit preserving. So whatever you have, yeah, these are small Cartesian categories. You ask the functors to preserve that structure. Yeah, finite limits, or these are also known as Cartesian functors. Finite limit preserving functors are also known as Cartesian functors. Okay, so this is a two category. Yeah, if I have to say it correctly, it's a two category because the objects themselves are categories and the morphisms are functors between them. On this side, what I have, the objects are locally finitely presentable categories. Okay, so I have to go to the next slide to explain to you what is LFP. LFP stands for the category has all limits exist, plus there is, so these are all large categories. Yeah, if all limits exist, the categories are large. They cannot be a set in general. So there exists a set of objects which we call finitely presented objects. There exists a set of objects that generates each object under directed colimits. Okay, so what I'm saying, yeah, this has to do with size issues. Okay, the category is large, but it is controlled by a small set, in the sense that every object can be written as a directed colimit of only those things. Now going back just 2 slides, I will show you what I really mean. Here I said that every set can be written as a directed colimit of finite sets. Every module can be written as directed colimit of finitely presented modules. Every vector space could be written as a directed colimit of finite dimensional vector spaces. So all these categories are in fact locally finitely presentable. Do you get this point?
Just,
Yeah.
one small question. Suppose X is a infinite set.
Yeah.
Format is greater than the alpha.
Yeah.
Then it is not finitely presentable.
It is not finitely presentable. In the category of sets, an object is finitely presentable if and only if it is finite. Yes. Yeah. For that, I should probably give you the definition. So let C be a category with directed colimits. This is important. Then A in C is finitely presented if home C A blank from C to sets preserves directed colimits. And this definition will turn out to be equivalent to finite generation and finite relations. Yeah, but this is very abstract. So let us leave this for now and let us come back to the bigger picture. If we know like that the category of vector spaces, the category of sets, modules, groups, posets, pre-orders, all of them are LFP categories. Yeah, that's good enough for us for now. And then let us write what are the morphisms between them. The morphisms I'm going to say, so they contain all limits and all colimits in fact. But I'm going to ask for the morphisms to preserve, so the functors between them, preserving all limits and directed colimits. Is this a surprise? Not really. We already saw that in the category of sets, finite limits commute with all limits and directed colimits. So I'm only asking on the other side for the functors to preserve the rest half. And this is what gives you this functor now. So CT, yes, the syntactic category CT is an object over here. Now I can take all Cartesian functors from CT to sets. This is my models functor. Mod blank. As we know, it has to be contravariant. Because if I put more restrictions, more axioms, then the class of models will shrink. So it is a contravariant functor. All Cartesian functors from a Cartesian category to the category of sets. That is my models functor. It will land inside LFP. And on the way back, I will say it is all the LFP functors. Yeah, all the LFP functors back to sets, which means all the functors which preserve all limits and directed colimits back to sets. This is my TH blank functor. The common theory is in fact given by this functor. Now, what was the property that I mentioned in my first lecture for stone duality? Do you remember? There was something special. Anybody? What were the functors in the stone duality? Blank 2. Blank 2. Yeah, home blank 2. Boolean algebra homomorphisms to 2. Those are filters. And Boolean algebra and continuous maps to discrete 2-element space. So that object 2 was playing a dual role. Same thing is true here. All the functors to sets and all the functors to sets. The category of sets is a Cartesian category, not a small one, but it is a Cartesian category, and the category of sets is also LFP category. And if I view it as only the green arrows, then I don't need both the functors are contravariant, but I can put cart op anyway. And this is the Gabriel-Ulmer duality. So just to reinterpret this, what I'm saying here is that I know it's 10 minutes. Thanks. Yes. So I will reinterpret this, that cart op is this syntactic manifestation of, I mean, the Cartesian categories, small Cartesian categories are the syntactic manifestations of Cartesian theories, and LFP categories are the semantic manifestations of Cartesian categories. So this is a perfect, this is one more highlight here. It is a perfect two-sided duality. Perfect two-sided duality in the sense that I can start with any Cartesian category, complete the circle. I will be isomorphic to the category that I start with. And if I start with LFP category, complete the circle, I will again be isomorphic to where I started with. Okay, so this is the syntax-semantics duality in the categorical form for Cartesian logic. And what lies at the heart of it, that in the category of sets, here I will write that. In the category of sets, finite limits commute with all limits and directed co-limits. This lies at the heart of it. This is what Mackay has termed as logical doctrine, which makes this work. If you go to a different fragment of first order logic, then you will get different things. So you will start putting more things on the syntax side, right? Fine. In addition to finite limits, so I still have some time, I can talk about that. For regular logic, what commutes with what? So say finite limits and images, the images are known as regular epimorphisms. These two together commute with, now something here will be reduced. So I mean all products and directed co-limits. So what will happen? That the corresponding duality would be, you have got regular categories, and here you have got so-called definable categories. So the functors are again same. The functors are reg blank sets, and the functor here on the back way is def blank sets. So these are all the functors which preserve products and directed co-limits. And regular functors preserve finite limits and regular epimorphisms. So that will give you that. This is also a perfect two-sided duality. And for the whole first order logic now, the whole first order logic. Wow. I managed to mess this up at the last moment. I don't mean to. For the full first order logic, this is again a result by Mackay. That you will get, this is op, I mean, of course, we have this op. You will get pre-toposis on one side. This I have been advertising already. Pre-toposis op. And on the other side, you will get ultra categories. So these are categories which have external structure borrowed from the category of sets. And here the functors are something, but they on one side they preserve pre-topos structure, and on the other side they are ultra functors. However, this is not two-sided duality, it is a one-sided duality. In the sense that from pre-topos, if you complete this cycle, then you are isomorphic to it. On the other hand, you have no idea, because we haven't identified the image inside ultra categories, the image of this functor. Yeah, that it's difficult to do that. So in that case, there are too many things on one side, not just finite limits, but also finite co-limits, like all finite products and regular epimorphisms. Lots of things are there on one side. On the other side, you only have directed co-limits and then ultra products. And therefore, this is not a perfect two-sided duality. I guess Lurie is working on this, Jacob Lurie. And this is the full first order logic duality by Mackay. This is also an old result. So logic, I mean, let me restate something that I said earlier. Yeah. The question is finding out the image of this functor. The forward from pre-toposes to ultra categories. What is the image that we don't know? Yeah, you won't get that isomorphism. This the category of ultra. Yes, this is a very large collection. Ultra categories is a very large collection compared to what we need. That's a single proof of Mackay of 100 pages. I haven't managed to fully finish reading it. He only managed to prove the one half.
If we know that, then there is a chance of finding out what the image is.
We know that the images should contain finitely accessible categories with directed co-limits, but that's all. And it should contain some ultra product structure. But yeah, not much more is known. It's one-sided. Yeah. He only starts with a pre-topos and reconstructs it from the category of its models.
I mean, what did you say? He constructed something which is not in the image.
Yes, yes. We know so many things. We know many things which are not in the image. But we don't know because, for example, as I said, accessible categories are necessary. Accessibility is a condition. So there are ultra categories which are not accessible. So therefore, we can rule them out. But yeah, apart from that, we don't know. Yeah, we have to make it smaller. We have to identify its image. Yes. Then we'll get a full two-sided duality. But that is considered to be a very hard problem. Even this one is difficult to prove. Well, I might add that this is a result due to myself, Rosinski, and then there was an error corrected by Tendas and Lack, Steve Lack from Australia. So
That was your postdoc work.
this is my postdoc work, yeah. This two-sided duality. Right, so an abstract logical theory manifests itself in different forms. One is syntactic form, the other one is semantic form. In fact, there is also a third one. Yeah, there is a triangle here. And that triangle usually consists of toposes. Yeah, toposes of certain kind. Like in this case, these are regular toposes. Then for the bottom one, we know the third vertex, that is all Grothendieck toposes. And they correspond to different logics. Yeah, geometric logic is at the heart of Grothendieck toposes. Regular logic is here. coherent, one can try. But the duality, like, I mean, this is not really disappointment, but the way you are working towards that, yeah, that is interesting, and that is the motivation. You want to set up a perfect dictionary between two different things. But once that dictionary is there, then you don't know what to do with that. And essentially, it's the same amount of information. Until you prove it, you don't know whether it is true. But once you prove it, you just have a perfect dictionary between two different areas, and it goes. After proving the duality, if you have one result on one side, then you can just translate appropriately to another side.
What is the consequence? That is what you are saying. Consequences will not move.
No, we can get all the consequences. We have a perfect dictionary, but then it doesn't remain as interesting. Once we know it exists, then it's not as interesting, in my opinion, at least. Yeah, like even algebra and topology dualities, which Nick and Marcus were talking about. Yeah. After you have, yes. Sorry, was there? Once we know that there is a perfect dictionary between those two fields, then there is nothing more to explore.
That is what the logician thinks. Just this duality must have some application in mathematics, right?
Yes, definitely. I mean, two seemingly unrelated areas are connected with the help of dualities.
Yeah, another thing also like that. Oh yeah, that's some like say in free topology, it is really hard to see what's happening. But you can see it in ultra-canary and then use your dictionary and come to the free topology and establish it. So that can be done, nothing more.
Just about like Galois theory, I want to give an example. Galois theory is connected with the groups.
Yeah.
Okay. Now, this is one-to-one correspondence. Fine. Okay. There the logician stops. Whereas mathematicians go one step further, telling because of this, for example, you cannot present an angle.
Right.
Which is not in the logic.
Which is not there in the logic. Yes. So, but logic provides a language. Category theory provides a language. So if you have a result in Galois theory side, then that will tell you something about the group theory.
Exactly. This is what
logician's job is to translate. That's all.
Now, what is the outcome of it? That is what I mean.
No, I think sometimes in natural language people used to use this duality. Like
Okay.
I'm not aware about it, but people are doing a lot of it. Like using duality in natural language things and try to see that how that logical argumentation will go on and use it in the artificial intelligence in some way, so that they can use it. So, but I'm not aware about this, but I know that some people are working on that.
And I can also add that
there are some implications in computer science.
Yes. Previously unseen results on one side.
Okay.
Yeah, like Deepankar in his talks was mentioning that Purvita can talk to Sujata via this functor. So the people are working in algebra, topology, totally different areas. But because of this duality, they have a way of communicating with each other. And if you have one result, new discovery on one side, that also gives you previously unseen result on the other side. And of course, I mean, the exact construction of this duality also plays an important role. How to translate? Yeah, any questions? Like this is the last talk. I just want to ask any questions.
So is there any, so as you said, different translations are possible between two different equivalents of categories. So
Yes.
are there any examples where two different translations have been possible in the past? Like between two categories, two different equivalences?
Like in Hilbert spaces, I don't remember this exactly, but C-star algebras and compact Hausdorff spaces. Yeah, that's correct.
That is, you take the function space on the compact Hausdorff space.
Yeah. So that is an example. I mean, those are previously unrelated area. Those were previously unrelated areas, but then because of this duality, you can translate areas from geometry to algebra, algebra to geometry. The perfect equivalence between, I mean, at the heart of algebraic geometry, what is there? It is still being used, that commutative rings and affine spaces. Yeah, there is a perfect duality between them. And we are still using this coordinate ring of a space and then the spectrum of that. So those things are being used, and those dualities are being generalized. And yeah, they lie at the heart of algebraic geometry, or I mean, analysis also, you have dualities. So they are useful. I'm just saying that from a category theorist perspective, unless you are looking for a new duality extending the existing one, you don't have much work to do. You just look for something new. In that sense, category theory and logic are like horizontal subjects. They don't grow vertically. They want to identify something on one side and two side, and then maybe look at their similarities and bring about those analogies in a perfect form, in a format. Number theory, geometry, analysis, these all grow vertically. They grow deep. But these subjects, they are horizontal subjects. They get across sections of mathematics, different sections, and they want to see the similarities. Yes, there is one chat item. Yes, in principle, every adjunction induces an equivalence between two good subcategories. Correct. Yeah, a dual adjunction, the fixed points of a dual adjunction will give you a perfect two-sided duality. And that's precisely what I was talking about in this Mackay's result. That you don't know what subcategory it is.
Just like the topological characterization.
Yeah.
We don't know there exists, but we don't know.
Right. Any other questions? Quick questions. Okay. So thanks a lot to all of you. I mean, for surviving until this very end. And yeah, this is still not the end. This is not the end of all the sessions. Yeah, we still have student presentations, and I encourage all of you to be here to encourage the students. Yeah, we are excited, and we'll take a short 7-8 minutes break, and then we'll start at 11:45. Thank you.
Hello. I think the first talk will be by, first presentation will be by Anand and Krishnendu, right?
Yes,
So do you want to share your slides or like
Yes,
how you are
yes.
going to present?
I am
Okay.
going to share my slides first, and Anand will do the proof using the proof assistant.
I see. Okay, okay. So I need to make you the co-host, I guess. We need to make co-host, otherwise they can't.
You just use the screen sharing. You can enable the option that others participant can share the screen. You can just enable the option.
I see. Okay, that will be great, I guess. Multiple participants. No, okay, one participant. It's already there. So you can try to.
Where is
Yeah, you want to?
Krishnendu?
Yeah, it's.
I'm here.
Yeah, Krishnendu, can you switch on your?
Yeah, camera and as well like the you can try to share your slide first, then we can see that whether it is working or not.
Host disable the participant screen sharing.
I see.
Co-host बन.
Co-host
ए
बना
बाप,
दो.
एक मिनट यहाँ पे करते हैं.
हो गया. So now please try.
Okay. Can you see the screen?
Yeah,
Yes,
it's
we can.
visible properly.
Wait, let me go through it for 1 second.
Uh,
Yeah. Okay.
It's going to die, it seems.
Oh.
This one?
Yeah, sure. I
Okay.
was just trying to, because you were not here, I was trying to see.
Okay, so welcome once again. So the student presentations are going to begin with, a very tight schedule. Yeah, you have to finish. If there is one person, 15 minutes, two people, 20 minutes, three people, 25 minutes. So we are on a very tight schedule. So Krishnendu, you should take ideally only 10 minutes. So this is a journey through Unida Lemma by Krishnendukar and Anand Tadipatri. Krishnendu.
Yeah, so hi everyone. So what we are going to do is to give you the presentation on Unitas lemma. So what I'm going to do is give you an overview through Unida lemma, and what Anand will do is to is writing down the proof using the software called Proof Assistant. I guess he will give you the proof by that. So the things which I will cover is first what a functor category is. Then I will go through Unitas lemma. Then we have Unitas embedding, which is the direct consequence of Unitas lemma. And then I will show you that Cayley's theorem, which for groups, which you find is precisely the application, the direct application of Unitas embedding. And then Anand will do the explanation part for the proof of the lemma. Okay, so first we have what a functor category is. That is, if you have two categories, C and D, we can define a category associated to that, that is where your objects are your functors from C to D, and morphisms are natural transformation between these two functors. So this is that, and this is denoted by D to the power C or CD within this third bracket or square bracket, whatever you say. This is a functor category between C and D. Then next we have Unitas lemma, and which states that if you have a functor f such that C2 set where C is a locally small category, then for any object in C we have this bijection. And note that this is a set bijection because we are landing in the category of sets. So the Unitas lemma tells you that in the natural transformation between this covariant home functor to f are precisely in one-to-one correspondence with the elements of FC. So this is that's all written here, and what more is that, see, note that I didn't start C to be a small category. So this set of natural transformations, we are considering the home set of functor categories. See, all the home set will be the natural transformation, of course, and this set may or may not form a set. So may or may not form a set. What Unitas lemma gives you that precisely this collection is a set. And resembling that, we have the dual version of the Unitas lemma. So where we don't take instead of taking this covariant home functor, we take the contra.
Can I ask this one? What is locally small?
If your home set makes a set, for each object, this set, if this is a set for you, this is a locally small. Okay, and if it is small, if the whole home set makes a set. Okay, so the contravariant version of that is that instead of taking the covariant home functor, if we consider the contravariant home functor, dually we have this thing. This is just the dual version of that, just some maneuvering of that. Okay. Then we have, if we consider this functor, that is C cross C2 set, this functor category 2 sets, where C comma F takes you to FC, and this functor, that is same domain and codomain, where C comma F goes to the natural transformations. So what Unitas lemma gives you that these two functors are actually naturally isomorphic. Okay. Then I'm using some notation to make our life easier. That is, the covariant home functor is denoted by H subscript A, and the contravariant home functor is denoted by H superscript A, and the natural transformation HAF is precisely this set. Just some notations. And then if we replace HB, recall this is your HA and HB is similar. HB in place of F in the Unitas lemma, we have this isomorphism, which says that the natural transformation between HA to HB is basically the home of B to A, the functions from B to A. So given any morphism from B to A, we can associate a function from a natural transformation from HA to HB. We call this H lower star or home F dash, whatever. Then what we can do is to associate C in every object of C to a functor to a home functor HA, and we associate F to this home to this natural transformation F lower star or a home F dash, and this gives you a contravariant home functor from C to C set, this functor space. We can interpret this as H lower star as C of to C set, and dually we can, if you consider the contravariant version of the Unitas lemma, that is considering the contravariant home functor, we have this isomorphism, and in this, and using this, we can define similarly H upper star, which is again a covariant functor from C to C of to set. Okay. So how Unitas lemma plays a crucial role here is to giving you this result, which says that these two functors, H star and H lower star and H upper star, are actually fully faithful. So we can say that every locally small category C is equivalent to a subcategory of the functor category of C, or dually we can say that the opposite category of C is isomorphic to subcategory of C comma set. Okay, and the morphisms are called, and the functors are called unit embedding. So yeah, this may look like to you the Cayley's theorem, which you learned in group theory, which states that every finite group is actually a subgroup of a symmetric group. What I'm going to show in the next slide is that Cayley's theorem is just a special case of Unitas embedding. How? For that, we need to first recall what a group is in terms of category. So recall that a group is a single object category, where object is your single object denoted by this star, and your elements are your group elements. And and morphism between these two and star to star are your essentially group elements. Okay, we are calling this category C. And since this is only one object, so note that a functor from C to set is taking your start to S, and a morphism from start to star, that is your group element, it's taking that morphism to a morphism to S to S. And by using the group property and the functor property of F, you can tell that this morphism is actually a bijective map from S to S. So you can associate F to an object, to a set S, and a group homomorphism from G to permutation of S. All right. Then if you consider, that S is essentially a G set. Now, what would natural transformation between these two functors would look like? That would look like this, that a set function is such that S to X with this property. And if you wonder that where I'm getting this from, this is, if you recall the definition of natural transformation, we have to commute a square. And if you precisely put this F and do the commutation in that square, you will get this result. That will give you that home star comma dash is essentially a group endomorphism. That's all written here, that covariant home functor, if you consider this corresponds to action on G by left multiplication, and the contravariant functor would be precisely the right multiplication. And I'm just considering the covariant here. And if you put F in place of Unitas lemma, you get this thing. And this thing is your basically G, because you are working in the category of C, and your left multi, and this set is precisely, you can check that this is essentially a group endomorphism. So what it says that the G is isomorphic to this group endomorphisms, which is a subgroup of permutation of G. And recall that this is precisely Kelly's theorem. So what we have done is to prove that these Unitas lemma is essentially the generalization of what we have seen in Kelly's theorem. Next, we have some other corollaries. If we have considered
2 minutes, Krishnendu.
Yes, just 2 things. If we consider X comma T to be a topological space, a presheaf F of set is defined to be a contravariant functor from X to sets. You can define on any category, to be honest, a presheaf, but I'm just using for sets now. And recall what a representable functor is. I'm denoting representable functor, representable presheaf by this notion. And by Unitas lemma, we have this thing. So what it tells you that if you have given a presheaf and given a representable presheaf, the natural transformation between them is precisely this set. So this is important because often understanding a topological space is often understood by the functions related to by the presheaf related to that space. And from a presheaf is important because it gives you very nice structures of that space, because presheafs of an abelian category essentially mix an abelian category. It is true for sheaves as well. So it's an important result. That's all. And Unitas lemma gives you this natural procedure to enlarge the pre-additive category. Unitas lemma is also true for pre-additive category, by the way. So if it essentially gives you from pre-additive category, you can enlarge to a pre-additive category, which is basically an abelian category. This is an article in Wikipedia. You can just look it up. So that's all I wanted to say. These are some references which should be, I hope that this whole slide will be on the website. And from now on, Anand will present and gives you the proof regarding that. I'm stopping my sharing.
Anand, we would like to see you, yeah, while you are presenting. Is Anand here? Yeah, he is here. Anand, please unmute yourself. Krishnendu?
Yes, sir. I'm trying to contact him.
Yeah, try to call him.
Sorry, my Zoom crashed.
Uh, am I audible?
Yeah, Anand, are you there?
Yeah. Am I audible now?
Yes, you are audible.
Yeah, I'm really sorry. My Zoom crashed. Like just when I tried sharing my screen.
Okay.
Yeah,
Yeah,
I'll
please
just share
share
my.
your screen.
Yeah.
And we would like to see you as well. Are you there? Yes, Suyash, please start. We'll put him on hold, let him reconnect. I hope only 1.5 board is enough. Yeah, we don't want to change the settings often. Yeah, change the camera angle. What is the topic? Okay, so because Anand is having problems with connection, Zoom connection, so we'll start with the next presentation by a group of 3. So that's Suyash Srivastav, Vineet Sinha, and Bhargav Kale. And they are going to talk about chains and anti-chains.
Yeah. I just wanted to
Please.
mention that I can see the option to share my screen now.
You have to use the mic.
Am I audible now?
Anand, we are putting you on hold. You can do it a bit later.
Sure.
We have started with a new one.
Yes. Okay. That's fine.
Yeah? Make
Yeah.
sure your audio, video, everything is working properly, and join again in like 15 minutes.
Okay.
Yeah.
So Bhargav will share the screen.
Yes, Bhargav, you be ready. Okay. Anand, you can stop sharing. Bhargav, please share your screen.
So a chain is a totally ordered subset of a poset. The width, the height of a poset is defined to be the size of the largest chain in the poset, and similarly an anti-chain is a subset of a poset such that any 2 distinct elements of that set are incomparable. So width is defined as the size of the...
Is Suyash audible to everyone in the audience?
Yes.
Yes, okay, thanks.
Width is the size of the largest anti-chain of the poset. We can define chain covers and anti-chain covers. A chain cover is a family of chains such that union of that family is the entire poset. I'll denote this by the chain covering number. The chain covering number is the size of the smallest chain cover of the poset. So a very simple reasoning can show us that the width of a poset is at most the size of the chain covering number, because if a poset has width m, then there exists an anti-chain of size m, and if f is a chain cover of that poset, then each chain can contain at most one element of A. So we would require at least m chains to cover the entire poset. So from this we get that width of the poset is greater than equal to mod of f for every chain cover. So basically less than equal to. Okay.
Talk to us and show us.
So this is less than equal to the chain covering number of the poset. But now Dilworth's theorem tells us that, so from this we get that we need at least width many chains to cover the entire poset. But Dilworth's theorem tells us that width many chains actually suffice to cover a finite poset. So This we will show by induction on the cardinality of P. If size of P is 1, then this is trivial. So if size of P is 1, then this is trivial because the width is 1 and one chain suffices. So let us assume that the statement holds for P less than equal to n. The statement is that if width is m, then m many chains suffice. So suppose width now suppose this suppose we have the statement for this is the inductive hypothesis that this statement holds for all posets with size at most n. Now take a poset with size n plus 1 and we will use induction to show that W of P is equal to C of P. Okay, so first of all, we will notice that the set of all maximal elements of P is an anti-chain. It is a maximal anti-chain. Similarly, minel of P is also a maximal anti-chain. So we will use two cases. We will deal with this in two cases. The first case is that there exists an anti-chain A which is not equal to Maxwell or Minel, and A has size m, which is the width of P. So in this case, consider the sets A plus, which is just the set of all elements of the poset which are greater than some elements of A. And similarly, consider A minus equal to the set of elements of the posets which are less than some element of A. Note that neither A plus nor A minus are equal to the entire poset because Maxwell of P is not a subset of A plus because A is not equal to Maxwell of P, and the only anti-chain containing Maxwell of P is Maxwell of P itself. So since it is not equal, it is not a superset as well. So therefore is not a there exists m maximal in P which is not in A. So it will not be an A plus as well. Similarly, since Minel is not a subset of A, we get that there exists a small element in this which is not in A minus. So both of these are proper subsets of P, and so we get that mod of A plus and mod of A minus are both less than mod of P, and by induction we can find chains. We can find omega P many chains which cover this and omega P many chains which cover this. For each such chain, suppose Ci and Di are such that this is equal to A plus and union of this is equal to A minus, then I notice that each element of A is in exactly one chain in A plus and exactly one chain in A minus. So suppose A is equal to A1, A2 up to AN, and A1 is in C1 and A1 is in AI is in Ci and AI is in Di. We have just renamed the chains according to which element of A lies in them. and then A is equal to union of Ci union Di, which are M many chains. So we get the claim for first case. Now for the
Can you wrap up in a minute? Yeah. Can you wrap up in a minute?
Okay.
Yeah.
For case 2, we can for case 2 we get that there is no anti-chain which is not Maxwell nor Minel and has size m. So no chain other than Maxwell or Minel has size m. For this, take x in Minel of P, and then there exists y in Maxwell of P, which is greater than x, because this is a finite set, such a y must exist. So we will remove the chain x comma y from P, the 2-element chain, and then we get a new poset which has no chain of size m. So omega of P prime is less than equal to m minus 1, and mod of P prime is strictly less than mod of P. So by the inductive hypothesis, we can decompose this into m minus 1 chains. And when we add the chain x comma y to it, then we get a decomposition of P into m chains. So this gives the whole proof of Dilbert's theorem. Timing.
Vineet, you may start. Yeah.
So now we will generalize the Dilbert's theorem in case of infinite partial orders. So, so for that we need to mention a theorem proved by De Bruijn and Erdos. Is it visible from? So it is De Bruijn-Erdos theorem. So it states that for any graph G equals V, for any infinite graph, if every finite subgraph of this graph graph G prime of G can be colored with K colors, then the whole graph can be colored with K colors. Can be vertex. We are here talking about the vertex coloring of the graph. So it's not the edge coloring. So it's important to mention this. So I won't be proving this theorem, but it can be proved by compactness theorem. we just have to create a theory for this whose every finite subtheory is consistent, then the whole theory will be consistent. So it can be proved by compactness theorem. So now the generalization of the Dilbert's theorem is this. If the maximal length of antichains in an infinite partial order p comma less than equal to is k, and this k needs to be finite. This k belongs to natural numbers. So then p can be partitioned into k chains. So first we will define a graph. G equals v comma e such that the vertex head is just the element of that partial order, and v1 and v2 are connected. V comma u is connected if v is if v and u can't be compared with each other, like v is not less than equal to u, and u is not less than equal to v. So notice that the vertex coloring of this graph correspond to the partition of that graph into the set of antichains. So if we have a coloring of this graph,
Vineet, is it possible if you can give just the idea of the proof and not prove it?
Yeah. So the vertex coloring of this graph corresponds to the partition of this graph into chains. So for every finite subgraph of this graph, because by Dilbert's theorem we had already proved that every finite subgraph of this graph can be partitioned into k chains. So every finite subgraph can be vertex colored with k colors. So then by the De Bruyn-Ardouche theorem, G can be colored into k colors, which is just equal to partitioning this graph into k chains. So that is the idea of the proof. And then one important remark, that this k needs to be finite. There is a result which I should mention here. If k becomes infinite, for any infinite cardinal kappa, if the
Give Bhargav some time to talk. You have 7 minutes left.
so
Total.
so Bhargav won't be talking.
He won't be talking.
No,
Okay.
he was just present.
Okay, fine.
So can I go through its proof?
You said already. Complete the remark.
So okay. So for any infinite cardinal kappa, there is a there is a partial order p comma less than equal to such that the maximal anti-chain of P has omega cardinality but any partition of P into chains is greater than equal to kappa cardinality. So we can't generalize this theorem further into cardinals. K needs to be finite by this remark. And yeah, is my omega is the first, the countable cardinal. Yeah, if there exists a partial order such that the maximal anti-chain is omega cardinality, but the chains can only be partitioned into kappa chains. Yeah. I don't know how we get this remark. But this is a result. So I have some time left. So do I 3 minutes? Okay. So I can't prove anything.
You did a good job of telling us the summary. So I think that's enough.
Yeah.
Yes. So let's thank this group.
I just want to mention one thing.
Yes,
the way we have Dilworth's theorem, so we also have dual of it, which is known as Mirsky's theorem, which deals with. So we saw maximum size of an anti-chain is equal to minimum number of chains in any chain cover. The dual theorem of this is maximum size of a chain is equal to minimum number of anti-chains in any anti-chain cover. So the proof of that is also very similar to the idea behind Dilworth and infinite Dilworth theorem. So just wanted to mention it. That also.
Okay, thanks a lot. Sujata, do you have any comments? This was your topic.
I'm very happy.
Yeah.
Thank you so much for the very nice presentation. Thank you.
Good. Thanks, Sujata.
Thank you, ma'am.
And thanks to all the presenters. So do we have Anand here? Thank you. Anand?
I'm here. Am I audible? Hello.
You are audible, but very weakly audible.
Okay, I'll see if I can change some settings.
Yeah.
Yeah.
Now it's okay. Let us switch off the lights.
Is it better now?
Yeah, it's better.
Okay. If this is fine, then I'll start. How much time do I have?
10 minutes.
Okay. Okay, so I'll start. So I'll be explaining unit dilemma, continuing from where Krishnendu left off. I'll be doing this in what's called a proof assistant. It's a software that helps you write logical arguments step by step in a clean way, and it helps you in the process. And what I have here is an implementation of the language of category theory in this proof assistant called Lean. So before jumping right in to unit dilemma, I'll give an outline of what we have here, the basic definitions of category theory and the basic constructions. So the first thing we start off with, of course, is the category. Category consists of objects. So ob is a set of objects, but I've written type because we are in the foundations of type theory. For our purposes, types and sets are more or less the same. So I'll be using types and sets interchangeably. And we have a hom set taking in two objects and returning a set. And we have the usual things, identity, composition, and so on. We also have these rules that a category is expected to satisfy. Composition must be associative. Identity must behave as a left identity under composition as well as a right identity. So here's the first example of a category.
Anand, is it possible that you can change the background, like from dark mode to bright mode, perhaps?
Yeah, I'll try that.
Yeah.
Is it better now?
Yes, this is better. Thanks.
Yeah. So here's our first example of a category, the category of types. A type is nothing but a set. So keep that in mind. The objects are types, and the hom classes are the sets of functions from A to B. Identity is identity, and composition is the usual composition. So here, now we need to check that composition is associative and all the usual rules are satisfied. And you see some strange sequences of symbols over here. I'll briefly explain what these are. So in a nutshell, these are called tactics. These are high-level commands that simplify down to proofs that the proof assistant can read and understand. So what we've done here is we need to prove this complicated thing. It's an unsimplified expression, but we can simplify it step by step. First, we introduce all the relevant variables, and we get a slightly less complicated, but still complicated expression over here. But then this is true by definition. This happens to be true by definition. So we ask it to prove it by reflexivity, and it's done. This is accepted by the computer as a valid proof. So you see our work of proving that composition is associative amounts to writing roughly 2 words. And we'll see examples of this throughout. So after categories, we have functors. Again, the usual things. This is the map on objects and the map on morphisms. Usually these are seen as the same thing by abusive notation, but they're made explicit in the proof assistant here. We have the usual rules that identity is preserved and so is composition. And that concludes functors. The next natural thing is to define natural transformations between functors. So again, you have a function giving you the components, and you have the condition of forming commuting squares. We can also look at some specific examples of functors. One is the identity functor from any category to itself. We can compose functors. And with these two, we can actually define the category of categories. Note that we're in the foundation of type theory. So the usual drawbacks of set theory do not bother us. So we go ahead and define the category of categories, where objects are categories. Hom sets are sets of functors between two categories. Identity morphisms are the identity functors, and composition works by functor composition. And it's not too hard again to see that all these actually satisfy the rules of a category. And that concludes this part. Now we'll look at some constructions that we can do using categories. The first and probably most important one is to dualize a category. We take a category and we construct its dual with the same objects, but with the hom sets reversed and composition reversed. This satisfies the usual rules. And you see it here, it follows from the fact we're crucially using the fact that C is a category. And by just using the definition that C is the category and using right identity for left identity over here, we can see that these are true by definition. And here's a small example, which I'll skip. Another construction of interest to us is the left hom functor. This will be crucial in the proof of unit dilemma. Here this is a functor which takes objects. So it takes objects to, so you can write this out more explicitly as this. So the object map takes an object X to the Hom set A comma X, and it takes a function F to a function which is post composition by F. You see, I can put brackets over here to disambiguate this. So it's a function which takes in another function and post composes with F. So that's how it works on objects and morphisms. And this is a valid functor, as we can see over here. Lean accepts these proofs, so we know that they're correct. And that was the covariant Hom functor. We can also define a contravariant Hom functor very similarly. So instead of taking X to Hom AX, we can take X to Hom XA. And this time, instead of post composing, we'll pre-compose. And again, with a little work, we can show that this indeed is a functor. All right, and here's our next big construction, a functor category. Given two categories C and D, we define the functor category to have objects as functors themselves. Morphisms between these functors are natural transformations, and the identity morphism is the identity natural transformation, and so on. Again, these form a category. And now we're in good shape to take a look at unit lemma. So what does it say? So this is the covariant version of unit lemma. Let's start off with this first. So what this says is that given a category C and a functor from C to category of types is nothing but the category of sets. I'll use types and sets interchangeably. And if we have an object A, which is an object of C, then we have an isomorphism between the natural transformations between this Hom functor, Hom A functor, and the functor F we're considering, and the objects and the elements in the set or in the type FA. So this is a lot to take in, but the proof is very simple. So you see, unit lemma is fundamentally not hard. The reason it feels complicated is because it's layered on at least 5 layers of abstraction. We're at objects, morphisms, categories, functors, natural transformations, Hom functors, and so on. And so it's a lot to take in. And that's where proof assistants come in. They guide us through this step by step so that we can systematically keep track of details without losing sight. So that's exactly what I'll do now. I'll sketch parts of the proof. So here, let's look at what we need. So we need to construct an isomorphism. So an isomorphism basically requires an arrow going from here
Anand, you have 2 minutes.
Okay, here to here and back. So let's do this. So we need to construct a map from here to here. So let's assume an arbitrary natural transformation, eta, let's call it. And now we are left to construct an element in the image of FA, in the set FA. But then we have the natural transformation. Natural transformation takes us from Hom A to FA. So I'll go along the component of the natural transformation. And let's see, we need to construct an element in Hom AA. But then we can just use the identity element of the category, which we know is for sure in Hom AA. So that's a short example of how we can construct a proof. I'll be brief here because I don't have much time. But you see, like, the details can be verified and proofs may look long, but you see it's just introduction and like a bunch of it's just unraveling the definitions. And we have a contravariant version of unit lemma similarly. And as a corollary, we can derive the Unida embedding. There's an isomorphism between these functors and the Hom sets, the natural transformations between these functors and the Hom sets. And in the 1 minute or so that I have left, I'll describe some attempts at automating parts of the proof. So here's the statement of Unida lemma specialized to the category of types. So here we are given a function from the category of types to itself. We're saying eta is a natural transformation. This is Hom AX to fx, and we need to produce an element of fa. So on its own, this might be a little too complicated for the computer. So I'll specialize to the case where x is a. So I've specialized to the case where x is a over here. And now using a function that I wrote, I try to find a proof, and it looks like it succeeds because there's a green arrow underneath. So if we want to look at the proof, it's over here. Notice that we use the identity function in the proof, and the computer has come up with the identity function on its own over here. Fun a, that's the identity.
Time is up.
Okay, yeah. And similarly, you can do the same thing in the reverse direction. That's all I have to say. Yeah, I can take questions now, or I can also take questions by email.
Which language is this exactly?
This is called Lean. Lean
Lean language.
Yeah.
And there was a question whether this is functional programming.
Yes, it is functional programming.
Yeah.
Yes.
Okay.
Yeah.
So let us thank Krishnindu and Anand.
Yeah. Thank you.
We have the next presentation by Nupur on cylindrical algebras.
Am I audible? Okay. Okay, sorry. So I will be talking about cylindric algebras. So far, we have seen that there's this tendency to algebraize logic. So we have seen that when we have propositional logic, we can convert that into a Boolean algebra. And then when we have intuitionistic logic, we can convert that into a Hating algebra. And the usefulness of doing something like this is that you can move from logic to algebra, and you can prove things about the logic using the algebra. So that makes things a bit easier for us. And also, these algebras have a usefulness in and of themselves. So Boolean algebra is also used separately, and you can construct Boolean algebras without even talking about logic ever. So we can do a similar thing with first order logic or predicate logic. And for that, what we use is cylindric algebras. There are also other formulations. I will not be talking about those. So there are some specific versions of cylindric algebras. For example, there are cylindric set algebras, there are cylindric algebras of formulas, and then there are the general cylindric algebras. Now, it's easier to understand cylindric algebras when you talk about them using sets, so I will do that first. So when you're talking about a cylindric algebra, what you need is a set, which we call U, and then we also need an index set, I. And then this is, of course, the set of all functions from I to U, or you can also consider it as the set of I index sequences of U. So for my example, I will use I will take U to be the set of real numbers, and I'll just take the finite index set 3. So I end up with the Euclidean space, the Cartesian space, 3-dimensional. And now, okay, so I have something like this. Now, what I will do is I will consider the power set of this. So all the subsets. Now we know that this forms a Boolean algebra, right? Under intersection and union. So intersection, union, then you have the empty set, and you have the entire space. So a cylindric algebra is first and foremost a Boolean algebra. So this forms the Boolean algebra. And it has, of course, in a Boolean algebra, we have these two distinguished elements, right? We have the 0 and we have the 1. But when you're talking about cylindric algebras, you have even more distinct elements, or the constants. So we will call those the diagonal elements for, so we have Dij, or I will write this at the end. where I and j come from the index set. So what is the diagonal element? A diagonal dij is just defined as all of those elements of the power set. So all the sequences or triples in P are, or no, I'm sorry, by all of the triples of R3 such that xi equals xj. So for example, the diagonal sets of R3 are easy to see. If this is my x-axis, this is my y-axis, this is my z-axis, then this is one diagonal line, and then the diagonal plane D12 is just going to be this plane, right? This plane that passes through the line x equals y. And similarly, D23 and D13 are also going to be planes like this. And of course, Dii is going to be the entire space whenever you have Dii, right? So we have these particular subsets of R3. And then we also have some special operations besides these two. So we call those CIs, right? So what is CI? This is actually the cylindrification operation, if you will. So this acts on elements of the power set. So for example, if I have this circle, right? And this, my x is the unit circle on the xy plane. And I consider C3x, so 3 refers to the z-axis here. What I do is I look at the set of all the elements in the entire space such that except for the third element in that tuple, in that triple, the other elements belong to this. So basically I get the cylinder, right? So Cx, C3x is just going to be all of the elements. Sorry?
Cylinder over X.
Yeah. So this is just going to be all of the elements of R3 such that xj equals, okay, or I can just write it like this, x I r belongs to x for some r in reals. What this means is that if, or I should write this as 3. So if I replace the third element of the triple with any other element, I will get something that belongs to x. So that is just this cylinder, and that is where the name cylindrical algebras comes from. You just translate your set along the ith axis, and you get a cylinder of some shape. Right now, this gives you a cylindrical set algebra, right? And this satisfies certain properties. How much time do I have left?
8 minutes.
Okay, great. So I will write some properties here. Right, so the properties of a cylindrical set algebra are, first and foremost, it is a Boolean algebra. Then, of course, the cylinder generated by the null set is going to be the null set. So Ck is of the null set is the null set for each k. Then, and if I take the cylinder generated by any element along any axis, then that element is going to be a it's going to be a subset of that entire cylinder. Then I have that the cylinder along the kth axis, or maybe I should actually be writing alpha instead of k, because I is any arbitrary set. So the cylinder along the alpha axis of x intersection, this is equal to C alpha of x intersection C alpha of y. Then you have that this operation commutes. So C alpha C beta of x is the same as C beta C alpha of x. and there are just two more. So as I said before, if you take DII, you just get the entire space, which is your UI, right? And then whenever your alpha does not belong to some beta gamma, then the diagonal set beta gamma is you just take the cylinder along these two. And then lastly, whenever you have two distinct coordinates, then this is going to give you the empty set. So the cylinder along the kth axis of dk lambda intersection x, intersection the cylinder along k again of intersection x complement is going to give you the null set. Right, so these are the properties of a Boolean set, of a cylindric set algebra. There are a lot of them, but they are all easy to see if you think about it for a minute. So now we are supposed to be constructing this algebra from a certain kind of logic, from the predicate logic. So how do we do that? Suppose we are given any predicate logic. Just like we did for Boolean algebras, we constructed the Lindenbaum-Tarski algebra out of it by taking the equivalence classes of logically equivalent formulas and then taking conjunctions and disjunctions, defining conjunctions and disjunctions on those. We do a very similar thing here. So if we are given, say a theory, right? So we are given a language and we are given a theory over that language. So we have a set of consistent sentences over the language. Then we can consider all of the formulas over that language. And we will say that two formulas are equivalent modulo the theory if and only if they are equivalent. Right. So yeah, now we have the equivalence relation that we wanted. We can construct the set of equivalence classes of the formulas out of this. So maybe I can call that the formulas tau. And then you can see that I have conjunctions and disjunctions over here also. Right, so I have all of this. Then I have my zero element, which will be, I also have complement. I forgot to include complement here. I'm sorry about that. Yeah, we have negation. We have the zero element. We have the top element, which is the truth. And then how do we construct the, okay, so here you would have seen that in the first talk today, Sir was talking about how existential operators are actually projections, right? So this looks very similar to that, right? The cylinder that you got, if you project that onto the XY plane, you get your original set back. So the cylinder operation here actually corresponds to the existential operator. So whenever you take, oh yeah, by the way, what is your index set here? Your index set is going to be the set of propositional variables that you have, right? So of course, you need a cylinder operator for each member of the index set, and that is exactly what you're going to do. Since we have been considering that the set of propositional variables is countably infinite, I will use my index set as omega over here. And yeah, so we have an existential operator here. So this just corresponds to there exists xk, right? And then you can follow that by any formula that you want. Right. And then what does the diagonal element do? The diagonal elements just give you the constants which are so dij is just going to be xi equals xj. And then of course you're going to add these for all ij in omega, right? So this gives you an algebra which is very similar to that, right? So if you want to convert these, so just like we did in Boolean algebra, we started with we got the axioms for a Boolean algebra corresponding to the Lindenbaum-Tarski algebra, and then we generalize them to general Boolean algebras. We can do the same thing here. So what will we do? We have the C alpha operators here already. You will just replace all of the null sets by the bottom element. Your equality will become by implication. Your subset will become implication, and so on. So you can convert this set of axioms for cylindric set algebras into a set of axioms for cylindric algebras for formulas, right? And where is the connection between the two? So you have something called definable subsets of a structure, right? So if I have a structure, say I have the real numbers.
And time is up, Nupur. Yeah.
Okay, I'll just take 1 minute. So a definable set is just the subset of your entire structure that is defined by a formula. So suppose I have a formula, right? And I think this is the notation, but yeah, this is just all the elements of your real numbers such that your model, this is true in the model. Right? Yeah. So your definable subsets will actually just give you, two definable subsets are equal. So phi in your model is going to be equal to some psi in your model, if and only if they are equivalent. So your theory models, I'm using theory and model interchangeably, which is not a good thing to do, but I hope you understand what I'm trying to say. So if and only if this is true, right? If they are equivalent formulas. And yeah, so from there you can get to definable subsets, and that will just give you the cylindric algebra of sets. Right. Okay.
Thank you, Nupur. First order logic. Next we have. Oh, sorry. Yeah. So I said thank you by muting my microphone. Yeah. So okay. Sorry for that. So next we have Atri Bhaumik.
Yes, sir. Yeah.
Are you presenting alone or with Sagar?
No, I'm presenting alone. So
then you have 15 minutes. Please share your screen.
Okay. Yeah.
If you guys don't finish on time, then the offline participants are going to have hard time finishing lunch. We have just 1 hour of lunch break today.
Is my screen visible?
We are still waiting. Yes, now it's visible. Please do Control L so that we can see everything. Yeah. Okay, so your 15 minutes start.
Okay, just a second. Yeah. So today I'll be presenting on Zorn's lemma and its applications. So this is my outline. So at first I will give the brief introduction, how the history of the Zorn's lemma, and then I will discuss about that axiom of choice and Weyl-Alternate principle. So how these three are connected via Zorn's lemma and each other, and then I'll discuss about ultrafilter and the ultrafilter theorem, and then I'll discuss some more applications based on it. is a resultant set theory that appears in a non-constructive existence groups, like where we do not provide some like a solid example, but rather than we show that they exist. So this lemma is proved by Grotowski and also by Zorn. They proved this independently, like Zorn proved in 1935 and Grotowski on 1922. So and you see that the axiom of choice is a bit less evident than the rest, and we'll take a look into how Zorn's lemma and the axiom of choice and well-ordering principle are connected to each other. But while Zorn's lemma is originated on 20th century, it still retains certain amount of controversy and quote unquote controversy, and we'll discuss this in my last section. So like in this workshop we have already discussed, it is all well discussed, the partial ordering, what is that is reflexibility, anticipatory and transitivity, and totally ordered, like where any pair of elements can be compared, and we denote chain by a subset of partially ordered set where totally ordered, which is totally ordered by the induced order. And what Zorn's lemma says that for a non-empty partial ordered set P and ordering, if every chain has an upper bound, then P has a maximal element. So now I will discuss something about the axiom of choice. So informally, if I have to describe it, axiom of choice it just says that it is possible to choose an element from every set. But the formal definition is a bit mathematical, and here we'll at first define a choice function. So choice function is a function from the, here I mentioned the 2 to the power x. I mean, by this I mean the collection of all sets excluding the null set to the set such that f of s is belongs to the set for every non-empty set. Like for example, okay, sorry, here I think I have some typo. So here I mean that a equals to the power set of natural numbers, and the minimum function, like for any set, the minimum value will give us a choice function, and we'll see come to see that this function actually behaves very well, and it actually gives us from well ordering to direct relation to the choice function. So what axiom of choice is that axiom of choice asserts that on every set there is a choice function. So now I will discuss how we can reach to axiom of choice from Zorn's lemma. Just give me a second. So let X be a non-empty set, because in case of empty set, the result is trivial. So we consider the pairs YF consisting of subsets Y subsets of F and a choice function F on Y. So by Y and F a choice function, I mean that Y be the set of partly successful attempts to construct a choice function. So suppose we are considering Y and F as a choice function on Y. And now we introduce the partial order on this set. All such pairs defining YF is less than Y dash Y prime and F prime, if Y is a subset of Y prime and F is actually the restriction of F prime on the set Y. So this poset is non-empty, clear, because every singleton for any X we can the partial choice function exists. Now, if CB a chain in this poset, we'll define Y bar as the all this union of these all collections from this chain. So this this mechanism is quite actually helpful. We'll see in the various proof using Zorn's lemma, we use this type of proof that we consider an element which is union of all this union of all the elements from the chain. So am I audible? Hello. Hello.
Yes.
Oh, okay. Okay. So just
there is a question. I think we should take that.
Yeah, you should take that. There is a question in the chat.
The
Please
chat.
take that.
Yeah. Element from empty set is not simultaneous. Okay. Okay. Let me just finish this and then we'll look into that. Okay. So. Okay. So here Y bar I'm mentioning that all the collection of YF that belongs to this chain, and I'm taking the whole union as Y, and I'm F bar S I'm defining as Fs for any set S that is defined on the set S. So this Y bar and F bar, it it is an upper bound for this chain. And since we have constructed in this very way, and the ordering actually defines that the ordering holds in such way that the lower function, the lower part, the function is actually its restricted version. So hence, by Zorn's lemma, there is a maximal element, and suppose we call it YF. I think the notation may be a bit confusion. I'm just saying YF be a maximal element. Now, what we'll do, we will show that this is actually for X. That is, we cannot consider any element other. I mean, if we subtract Y from X, there will not be element. That is, Y is actually the total set X, and the F is exactly the choice function. So how do we proceed? We choose an element from X set minus Y, and that is, and then we can extend Y. So sorry again, this notation is wrong. There should be union. I have written intersection here. So Y union X, by defining the function Fs equal to X for any S containing X. So what we done, we actually extended our choice function F bar here. So this contradicts our maximality of this chain. So we cannot find any element from X set minus Y. And so we claim that therefore F is the choice function for our set X. So okay, something. Yeah. So next we will discuss something on the well-ordered set and the well-ordering principle. So by well-ordered set, I mean a poset which is well-ordered if it is a chain and every non-empty subset here has a minimum. So for example, we can consider natural number set as a well-ordered set. On the other hand, like the integer set is not well-ordered because we can consider the negative integers and there is no minimum element for any subset. So what well-ordering principle tells that the well-ordering principle asserts that every set can be well-ordered by a suitable relation. So let us take a look into that, how we can proceed from Zorn's lemma to well-ordering principle. Again, we are considering a non-empty set. And now here we define a term that the initial segment. So for a chain C, initial segment is a subchain that X, if X is less than a element Y in the subchain C dash, it will imply that X also belongs to the subchain. So we can see that the initial segment and the initial part of a chain, we can consider it this way. Now we're considering the pairs, the Y and with the ordering and consisting subsets of Y subset and well ordering we defined on Y. We define a partial order on the set, such a pairs, similar manner we have done in the axiom of choice, such as like we define that a set and the corresponding word ordering is less than a Y prime and the particular ordering respective to Y prime whenever Y is subset of the Y prime and the initial and Y is actually the initial segment of Y prime in the ordering of Y prime. So these two, that means in a informal term, these two orderings will agree on the set Y. We can view in that way. So since X is non-empty, the poset of course it will be non-empty, and furthermore, C we consider a chain C. We define again similar this construction again similar. We consider Y bar as the union of these elements from the chain, and we see that this ordering like X is less than Y will imply again Y bar. I mean the ordering for Y bar will imply that X will be less than Y for some ordering Y belongs to that chain. So we define that this is also a well ordering, and this so therefore the union of this we define by Y bar, and the pair is an this Y bar is an upper bound for the chain. So now again we'll use our Zorn's lemma. And
okay, you have 5 more minutes to wrap up. Okay.
Okay. So sorry. So this Zorn's lemma will contain a maximal element. We go again. The procedure is same. Again I have made some typo. This should be Y union the element X, and we'll define the same manner that the Y is actually the whole set X and the whole set X is well ordered. So okay, yeah. So next, we have in our workshop we have already discussed about alter filters, but the sense was there that the prime filter way. But here I will pose this thing as a more topological sense, and set theoretic sense. So a filter will already define that it is the upward close and the intersection is will lie with the filter, and we call alter filter that A is on the set, either it belongs to the filter or doesn't belong to the filter. So in this literature, I am noting it as this we call alter filter. So this is actually equivalent with maximal filter, but I've just noted here that we'll call a maximal filter is the filter which cannot be extended. So so this is basically the alter filter theorem, and we actually have done this in a tutorial session, but that's about prime filter. So the proof is kind of same. Again, we'll consider a chain, we'll again take the union, and we'll claim that this thing is also, because here the union is also filtered. The null set doesn't belong to the finite intersection, will hold it, and also upward close. So this chain will contain again an element, and we'll call this maximal element an alter. So like we can choose a filter, we can choose all filters it contains, it we take its union, we claim that therefore this is a maximal element for the chain, and we'll using Johnson again we say that there exists some alter filter that contains. So so here now I will discuss some more applications on of Zorn's lemma. So in topological spaces, we see that a topological space can be say that has a connected component. It can be proved using this Zorn's lemma. The procedure again is kind of similar. We'll consider a set of non-empty connected sets. We'll consider the set for any index that will the totally order this subset. And the ordering should be like the C alpha will subset of if otherwise like C alpha will subset of C beta, or the other way the C beta will be 0. So this union will be again connected because the sets are the sets are subset of one another. So the intersection will be non-empty. So this union will be connected. So I actually skipped that part that this union will be connected. So this union will be connected since the intersection is also non-empty. So using similar argument, we proceed that and we say that there exists a maximal component, and so therefore in a topological space we can say that there exists a maximal connected component. So next
to wrap.
Okay, ma'am. So next year I've just discussed the measurables existence of non-measurable sets. Actually 9105 Pitali described it, that taking the choice set by the equivalence class of rational number, we can construct a non-measurable set. Also here I described some other results where the Zorn's lemma has been used, like Tikhonov theorem. So the Tikhonov theorem where the product of any arbitrary product of compact sets is compact in the product topology. So here the construction includes Zorn's lemma, and also in algebra and linear algebra there are various results. I actually didn't provided the structure of this, but I just noted them that like in vector space has a basis. A non-trivial unitary ring has maximal ideal non-empty set can be given a group structure, and any algebraic extension there is a field homomorphism there where C is an algebraic closed can be extended to a homomorphism. Next, it is I think this the notion of axiom of choice give rises to some paradoxes. So one of the famous or quite popular paradoxes like the Banach-Tarski paradox. Actually, there is a very good book by Michael Wapner, I think, and the book's name is The P and the Sun. So here where he describes this paradox pretty elaborately. And so this paradox is essentially that if we take any closed ball and we can broke into 5 different parts, and we will rearrange it, we'll have 2 different spheres of same radius. That's actually where we can grow from a P to a from a small radius sphere we can grow to a larger sphere. So and this construction actually has been done by using axiom of choice from picking elements from ASO3 by this is the special orthogonal group. I mean the taking from the set of orthogonal matrix 3x3 orthogonal matrix who have determinant 1. So they actually represent rotations in a 3-dimensional space very well. So the construction is in such a way that they will pick a particular rotation type and they will deconstruct the sphere in
Please try
different
to
parts.
wrap up. The time is already over, Atri.
Okay. So that's all. And like I have described a problem here, but so I'll not go into its solution. So like if you have given a finite set of spherical planets and of same radius,
You can
and
send the
no to a,
slides and we will post them on the website so that everybody can read.
oh, okay, okay,
Yeah.
thank you. So,
Can you please look at the chat and address
yeah,
that
yeah, yeah.
question? Yeah,
Yeah.
please, quickly.
You need chain condition. Actually, here by chain condition, I'm considering totally ordered set. So I think that we need the totally ordered sense to construct. I mean, to use this Zorn's lemma. And sorry, I missed the question. Just give me a second. I'm just looking at the question. And okay, so yeah, he actually then posed commented on this. So I think
Okay.
he got his answer.
Okay, so in that case, let's thank Atri and Sagar.
Okay,
and
thank you.
Let's move on to the last presentation before the lunch break. Can you please stop sharing, Atri?
Yeah.
The last presentation will be by Bisham Devan, Debanjan Chakrabarti and Suyesh Pathak on complete lattices. Who is going to speak first?
Am I audible?
Yes, Debanjan, you are audible.
Okay, so I'm going to speak on behalf of all of us. So
okay. So would you like to finish in 20 minutes if you are alone?
Yes. Actually, the talk is a very short one. So I think it will be
Yes,
done by 20
that
minutes.
would be good for us to have lunch. Thanks. Please share your screen.
Sure.
And if possible, please switch on your video.
Let me first switch on my video and then share the screen. Not sure if the book works.
Yes, please press Control L.
Make the screen, I'm in full screen mode.
Check whether control works. Otherwise, read mode will do, I think.
Control L.
Control L.
Yeah.
Yeah.
Yes. Yes, you can start.
Okay. So essentially, we will be discussing about complete lattices, and most importantly, the fixed point theorem. We will discuss about some of its applications, and we'll later look into an algorithm which finds the fixed points of a complete lattice with respect to a monotone map. So let's define what is a lattice. I think the definition of lattice is very clear by the lectures we had till now. Still, for a recap, I'm going to define what is the lattice. So let's begin with a poset and A, and let B be a subset of that poset with the same ordering as some present in A. And we define the set of all lower bounds of B as B superscriptives, and similarly we define the sorry, I just mentioned the definition of the upper bound, and similarly we define the set of all the lower bounds of B, and the least upper bound of B. I mean, if BU has a list element, then that is the least upper bound of B, also denoted by LUB. Similarly, we define the GLB or the greatest lower bound, and we know that if B is a set of cardinality 2, if it has two elements, then the LUB of that set is denoted by X join Y, and similarly the GLB is denoted by X meet Y. So, similarly, for any arbitrary subset B of the poset A, we define the LUB of B as join B, and we denote it by join B, and similarly the GLB is denoted by meet B. The definition is exactly, we shall see what the actual definition is. It actually is the least upper bound of all the elements present in B. We take its least upper bound if it exists, and similarly we do it for the greatest lower bound. So we take all the lower bounds and then we consider the we consider the GLB. So we define what a lattice actually is. So essentially, if we, for any two elements, if we have the join and meet existing in a given poset, then we consider the poset to be a lattice. And if for any arbitrary subset B of the poset A, if the join and meet exists, then we say that the poset is a complete lattice. Equivalently, if we define A to be a non-empty set, and we define these two operations, the meet and join, and take that the meet and the join, they are associative, they are competitive, and A meet A join A both at A, and like that, they this forms a lattice. We can actually verify that if A, I mean the LUB of A and B is B, then the ordering induced by it, that is, we say that A is less than equal to B if LUB of A and B is B, that is indeed a partial ordering. Just as I defined previously, that if for any arbitrary non-empty subsets of a lattice, or of order of posets, if the join and meet exists, then we say that the that the poset is a complete lattice. Now we define what is a fixed point. For fixed point, we need a complete lattice. We also need an order preserving map from the complete lattice to itself. What do I mean by order preserving map? That is that if x is related to y, then f of x is related to f of y. And we define the fixed point as an element x in A such that fx equals x. We also define the least postfix point and the greatest prefix point of f, and the postfix point is actually defined as those points where x is related to fx, and the prefix points related as are those points where fx is related to x. And fixed points essentially are those points where fx is equal to x. So a fixed point is essentially the postfix point and the prefix point. And the Naster-Tuskegee fixed point theorem actually says that the set of all the fixed points in a given lattice, they will, in a given complete lattice, they will indeed form a complete lattice, and the whose least element is actually the least postfix point, and the whose greatest element is the greatest prefix point. So this is the Naster-Tuskegee theorem, which was given by Tuskegee in 1955, and it was earlier given by Naster also in 1920s. A similar statement was there that if we have a complete lattice A with the ordering less equal to, for if the order preserving function f from A to A, the set of fixed points will form a non-empty complete lattice. We actually won't talk about the proof because the proof is readily available in the internet, and it's easy to prove by simply using the definitions of what the fixed points are and checking that the prefix points form a lattice, the postfix points form a lattice, and like that. So because primarily due to time constraints, we won't be going through the proof. Instead, we'll be showing that the fixed point theorem is used to prove two other important theorems, one in set theory and the other in topology, the Schroeder-Bernstein theorem and the Cantor-Mendelssohn theorem. So let's move to the proof of those theorems, which can be considered as applications of the fixed point theorem. So for proving the Schroeder-Bernstein theorem, we first prove the Banach's lemma, which says that if we have two inductive maps, if we have two sets A and B, and then we have two inductive maps F from A to B and G from B to A, then we have a subset S of A such that B, if we take out all the images of S in B and find out its complement in B, that is B minus Fs, and then take its image with respect to G, then that essentially is A minus S. So that is Manak's lemma, and this this is actually proved by the help of the Nassar-Tuskegee fixed point theorem. We can have a look at the proof with where we first construct the power set of A, and we order it by the set inclusion, and then we define this map, which is actually a monotone map, and by the fixed point theorem it has a fixed point S. Actually this S is the S which sorry, this is the S which we have to look to. And then by the help of Banach's lemma, we will prove the Schroeder-Bernstein theorem. So Schroeder-Bernstein theorem actually says that if A and B are two sets, if an injection from A to B and G is an injection from B to A, that means two injections exist, one from A to B and the other from B to A, then there exists a bijection from A to B. And this is actually the proof of Schroeder-Bernstein theorem, which uses Banach's lemma. We actually find the subset of S by the help of the Banach's lemma, and we can check that in S this definitely holds. Then we extend it to the entire A and check that it's indeed is a bijection. Now we move to the proof of Cantor-Bendixson theorem, which will prove by the help of this Nassar-Tuskegee fixed point theorem. But before going to the proof of Cantor-Bendixson theorem, we shall define some concepts of topology which are not discussed previously and will be required for this particular theorem. So if A is a subset of a topological space X tau, and we define the derived set of A essentially as the set of all limit points of A, and this can be denoted by A prime. Similarly, now we say that the derived set or the subset is perfect if it is exactly equal to its derived set, and we say that the subset A is said to be scattered if the only subset B of A for which the derived set is a superset of B, that is the empty set. That means for all other subsets of B, B is actually a perfect set. So what does Cantor-Bendixson theorem actually states? Cantor-Bendixson theorem states that every closed subset of topological space can be considered as a disjoint union of a perfect set and a scattered set. So here is an example. Here is an example of what it actually means, the Cantor-Bendixson theorem. For example, if we consider the standard topology on the reals, and then we consider the closed subset, which is the closed interval of -1 to 0 in union the set of natural numbers, then the perfect part of A is this closed set, which is the closed interval -1 to 0, and the scattered part is N. And here we present a proof of the Cantor-Bendixson theorem. So essentially we define B and then show that B is actually a fixed point with respect to the map which we defined as S. So S is actually an element of the power set of the X on which the topology is defined. So S is actually a subset of A, and S like that. So here we complete the proof. And now we discuss about the complexity of finding a fixed point. So we have a complete lattice, we have a monotone function, and now our target is to find at least one fixed point of that lattice. So there were algorithms. In fact, the clean iterative algorithm actually checks for the list element, what is its function, then where does the map takes to, then for that image where that map takes to, and like that. And if you have a finite lattice, we can generate the fixed we can generate at least one fixed point in order of L, where L is the size of the lattice. However, an algorithm was provided in 2008 which returns the fixed point in order of log L queries. And essentially what it does, it has a complete lattice which is given as the input. We have the monotone map which we use as an oracle. So we use the monotone map to query whether a particular point is a fixed point or not. And this particular algorithm returns a fixed point within log L10. So essentially what this algorithm does, this algorithm at first decomposes lattices. I mean, it actually finds all the maximal chains of our complete lattice, and then employs a binary search algorithm across the maximal chains. Although the binary search is not exactly guaranteed to return a fixed point in a chain, even if it is present in the chain, in this particular paper, it's shown that if we run the algorithm across all the maximal chains, then it is guaranteed to return at least one fixed point. Let us quickly look through the algorithm, which essentially is sort of the binary search algorithm. So we essentially consider the lower half and the upper half and check whether the fixed point exists in the middle, and then we find the appropriate half and continue like that. So this is a presentation. Is there any question?
Thank you, Devanjan. Any quick questions from anybody? Online participants? So I suppose you are just going to apply these algorithms over finite complete lattices.
Exactly.
Right. And if you really want to make sure you find a fixed point, then this algorithm is useful or not?
Like given a complete lattice, this algorithm is definitely useful because it is guaranteed to find a fixed point. But if we consider only a maximal chain instead of considering all the maximal chains, then this algorithm may fail.
Okay. In that case, thanks a lot to this team of Devanjan, Suyash, and Bisham. Let's clap for them. And this is the last session before lunch, and we'll meet here again sharp at 2:30. Thank you. Devanjan, you can stop sharing. Yeah, sure.
Thanks.
Thank you. Thanks a lot. So we are closing the meeting for lunch and then we will come back. Yeah.